Okay, I briefly mentioned before that we've got two questions centered around series. First question is, does the series converge? The second one, what does it converge to? We just saw a few examples of geometric series where we can answer both those questions. We can decide whether it converges or not based on the r value, whether it's bigger than or smaller than 1 in magnitude. If it's smaller than 1, it converges. If it's bigger than 1, it diverges. If it's equal to 1, it also diverges. And we can also answer the question about what does it converge to. It's a over 1 minus r in the case of the geometric series. It's not very often that we can actually answer that question about what it converges to. We can certainly determine whether a series converges or not, but actually finding the value to which it converges to is a challenging task. So geometric series are ones we can find the value to which it converges to. There's also another kind of series that we can find the value to which it converges to, and these are ones that are known as telescoping series. And that's what this next example illustrates. It's another series that we can actually find the value to which it converges to. So let's look at the kth partial sum. N equals 1 to k of 1 over n plus 1, n plus 2. Now we could split up the rational function that represents the term as 1 over n plus 1 minus a 1 over n plus 2. You'd use partial fraction decomposition to do that. And so what does this mean? Well, if I look at now the sum of the terms, it's putting n equals 1 in, so that's 1/2 minus 1/3 plus 1/3 minus 1/4. So the first two come from n equals 1, the next two come from n equals 2, plus 1/4 minus 1/5 plus 1/5 minus 1/6, and so on, all the way down to 1 over k plus 1 minus 1 over k plus 2. So that's the sum of the first k terms. And we see that a lot of collapsing actually happens. There's a negative 1/3 and a positive 1/3, a negative 1/4 and a positive 1/4, a negative 1/5 and a positive 1/5, and so on all the way down the list. And so what we end up finding is that even though there's a lot of terms being added together in the kth partial sum, there's this collapsing effect. It's often referred to as a telescoping effect, where the tail end and the front end actually collapse down and give you this nice compact form. And so the kth partial sum is this, and so now we can look at the limiting value of the kth partial sum, and that's the limit as k goes to infinity of 1/2 minus 1 over k plus 2, and we see then that the value has to be 1/2, because 1 over k plus 2 goes to 0 as k goes to infinity. And so we have that the sum as n goes from 1 to infinity of 1 over n plus 1 times n plus 2 is 1/2. So the series converges to 1/2. And again, let me just reiterate that it's not very often that we can find the value to which a series converges. Geometric series, we can find the value to which they converge, and also series of this form, telescoping series, where you can find a formula for the kth partial sum because of this collapsing effect. Finding a formula for the kth partial sum is generally a challenging thing to do, but for geometric series and these telescoping series, you can actually do it. For a general series, it may not be possible, but we can still answer the question about whether a series converges, and we're going to learn techniques and tools for doing that over the next few sections. In this next example, we're going to consider the series known as the harmonic series. And it's a series where the terms are of the form 1 over n. Now this series turns out to be really important. And so why is it really important? You may say, well, it diverges. At least that's what we're going to try to show. So if the series diverges, how could it be important to us? Well, it's because it provides an example of a series that can be used to test your intuition about what you know about series. Now, what do I mean by that? I mean, we've been looking at series, and we know that if we want our series to converge, then the terms eventually better get small. We better not add a lot to the very end. So as we keep adding in more and more and more numbers up, the numbers that we keep adding to our series better be getting smaller and smaller and smaller and smaller. And so this fits that property. 1 over n, those numbers get smaller, so the very tail end, we're adding little numbers on. Now, just because the numbers get small, it does not mean that they're not making a significant contribution to the sum. In fact, in this example, even though the tail end is really small, apparently they're not small enough because the series still diverges. And that's why this is really important, because it gives us an example of a series where the terms get really small, but apparently not small fast enough because the series still diverges. So let's show that this series diverges. And now we have to think about how can we show a series diverges? Well, the definition for a series to diverge is if the limit of the partial sums does not converge. If the limit of partial sums converges, then the series would converge. It would just converge to that limit. So what I'm going to have to do is look at the series of partial sums. And so let's look at the partial sums. And in fact, I'm only going to pick some of the partial sums. So I'm going to look at S2, I'm going to look at S4, I'm going to look at S8, and so on for partial sums of the form S sub 2 to the power of n. So this is 2, S sub 2 squared, S sub 2 cubed, etc. So let's see, what can we say about these things? So let's look at S4. I have 1 plus a half plus a third plus a quarter. Well, I can say, well, that's bigger than 1 plus a half plus, well, a third is bigger than a quarter. And now I notice that, oh, those 2 quarters combine together to give me a half. And so I get this is 1 plus 1 half plus 1 half, or 1 plus 2 halves. So the fourth partial sum is bigger than 1 plus 2 halves. I'm going to leave it as 2 halves rather than 1, just so I can spot a pattern. Now let's look at the next one. Well, we just saw that this was bigger than a quarter plus a quarter, so that's bigger than a half. Now if I group the next 4 terms together, each one of them is bigger than an eighth. So this is bigger than 4/8, which is a half. And so the partial sum, S sub 8, is bigger than 1 plus a half, plus the next 2 grouped together as a half, plus the next 4 grouped together as a half. So that's 1 plus 3 halves. And we can keep doing this. And I'm going to look at powers of 2 for my partial sums so that I can keep grouping 2, 4, the next 8, the next 16, the next 32, and I can keep doing this grouping. Now, there's no problem with doing this grouping because I've got an infinite number of terms. And so I can always keep grouping as much as I like. I don't ever run out of terms to group together. And so what I notice that for any individual partial sum, so S sub 2 to the n, I can do this grouping. And I get that, well, I actually get an inequality here. I get that it's bigger than 1 plus, and let's look at what happened in the previous case. So the first one was 1 plus a half. So in some sense you can think we started with a 1 and then we grouped the first term together with itself, so it was just one term. The next one we grouped the first term and then the next 2 terms. And then for the next one we grouped the first term, the next 2 terms, and the next 4 terms. And so on. And how many groups do I have here? Well, I have 1, 2, 3 groups that each gave me a half for the S sub 8 partial sum, but 8 is 2 cubed. So it looks like the number of groupings I get is just the exponent of the index for the S. So for this case, it looks like I'll get n over 2. So the sum of the first 2 to the n terms is greater than 1 plus n over 2. And so there's a general pattern that we have. So again, it was easier to work with these powers of 2 groups rather than each individual partial sum. So there's a lot of other stuff. There's a lot of partial sums going on in between these ones. There's S3 in between these ones, there's S4, S5, S6, and S7, etc. And I'm not going to bother working on formulas to try to figure out how big those things are. At the very least, I know S5, S6, S7, and S8 are bigger than S4, so I know they're bigger than 1 plus 2 over 2. And the next group, S9, S10, S11, S12, etc., up to S15, I know they're bigger than 1 plus 3 over 2. So I'm just going to focus on these checkpoints because they give me a way to figure out how big the partial sums are, at least as I move along the series. And so now from this, we can see why it diverges. So we notice that the limit as n goes to infinity of the 2 to the nth partial sum, so summing up the first 2 to the n terms, you get that, oh, there's an inequality here, you get that it's bigger than the limit of 1 plus n over 2. But this limit is infinite. So the sum of the first 2 to the n terms has a sum which is bigger than 1 plus n over 2, and so as n goes to infinity, the sum of the partial sums must be bigger than the limit of these things, which is infinite, so it must be infinite as well. And so therefore, Sn does not converge. The partial sums can't converge. They get big. And so the series diverges. The harmonic series diverges. Okay, so there we've got a proof that the harmonic series diverges because the partial sums don't converge. Now again, let me reiterate why this is an important series. It's an important series because it's a series that diverges, but the terms get small. So even though we're adding up small things on the very end, and we keep adding smaller and smaller and smaller things onto the tail end, they still make significant contributions, enough that it causes the partial sums to diverge, and hence the series to diverge.